Thank you for everyone for joining, whether it's morning, evening, or afternoon for you, regardless of your time zone. Thank you for taking the time. I just want to remind everyone that the Q&A feature is enabled for this webinar. So if you have questions at any point, feel free to put them there and we will get to them at the end of the talk. And then finally, the closed captioning is also enabled and you can turn that on with the button at the bottom of your screen. Um, Also, we always love hearing from you and what you want to hear. So if you have suggestions for future speakers in the series, we have a suggestion form on our website, and I will put the link to that in the chat right after this. We love hearing from you. It's always very helpful to have these suggestions. So I very much encourage you to fill out that form if you would like. Today, we are delighted to have Dr. Sean Gallen join us. He is an associate professor at Colorado State University, and his very multidisciplinary research involves process-based geomorphology, active tectonics, natural hazards, and more. We are delighted to have him here with us, where he will be sharing insights from the Hellenic subduction forearc. So without further ado, I will be turning the floor over to you. Thank you
All
so
right.
much.
Thank you. All right. I will share my screen and get all this started. Okay. Oops. I'm almost there. All right. So I just want to thank everybody for joining the webinar where I'm going to be talking about the role of upper plate faults in earthquake hazards and hazard interactions and cascades above subduction zones, with an example from the Hellenic forearc. I'd also like to thank SCNet for hosting this webinar series and being able to showcase some of the research that folks are doing, hopefully inspire other research related to subduction zone geohazards. So this work is sort of years in the making, with a number of different collaborators that are listed here. But what I first want to do is highlight the really significant or primary contributions from two former students of mine. Richard Ott, a former PhD student who's now a professor at University of Amsterdam, and then Elena Bruni, a former master's student who went on to do a PhD and now works for a consulting firm in Switzerland. They did most of the work of what I'm going to present today. So why I'm talking about this today is that subduction zone earthquakes occur not just only on the megathrusts that we have here. So this is just a schematic cartoon of a subduction zone, and I'm showing a hypothetical rupture patch along the megathrust. And megathrust ruptures and megathrust earthquakes are a very obvious focus for researchers because they produce the largest earthquakes on the planet. And this is a huge focus of SZ4D's goals, is to understand megathrust ruptures in particular. However, in terms of cascading hazards or hazard interactions, megathrust earthquakes may not always be the dominant player. So, of course, they can generate strong ground motions offshore and displace the seafloor and generate tsunamis. But in this hypothetical cartoon that I have here, the intensity of ground shaking from a megathrust rupture may not hit on land very hard, particularly where we have high topography, where we might expect slope failures and earthquake-triggered landslides. So this is an important thing to think about: is, do megathrust ruptures actually produce important secondary hazards in terms of slope failures? And that may or may not be the case. However, we do know that upper plates have faults, and in this cartoon, this poor city has been situated above this hypothetical blue fault here. And you can envision that if it ruptured, it's going to have a shallow rupture, and the intensity of ground shaking hypothetically would be much higher in the city that's there. And also you'd have higher intensity of ground shaking in high topography, where you can have secondary hazards such as landslides. So this is important to think about in terms of studying subduction zone geohazards, is thinking about this interaction between the intensity of ground shaking, where populations are located, and where high topography is located, to be able to think about whether or not those faults are actually going to impact human populations and what the cascading impacts might be. Another important thing that I'll highlight today is that not all subduction zones are strongly coupled, meaning that not all of them are capable of producing large megathrust type earthquakes, but all upper plates in active subduction zones have upper plate faults that are seismogenic. And so it's important that we understand these upper plate faults, even in settings where we don't think we can get these big megathrust earthquakes. So we're going to be going to the Mediterranean in the talk today. I didn't put in a global map to show you where this is located, but hopefully you know where the Mediterranean is. And what I'm showing here are just some of the major active and inactive convergent plate margins in the region. Today's talk is going to be broken up into two parts. The first part, I'm going to talk about the role of upper plate faults in generating large earthquakes and tsunamis in the Eastern Mediterranean. And the idea with this part of the talk is to highlight the role of upper plate faults in subduction zone geohazards and how they can have a profound impact and even generate tsunamis. The second part of the talk is a little bit different. What I'm going to talk about is land surface hazard cascades with a case study. And there, in this case, we do think it is related to earthquakes on these upper crustal faults. But more importantly, what I want to do is emphasize the importance of studying ancient but ongoing land surface hazard cascades as a complement to studies that do rapid response efforts. So studies that, after an earthquake or after a big rainfall event, go and monitor what happens after that event. Those are really useful studies, but we can also use the geologic and geomorphic record to gain an understanding of how landscapes respond to large perturbations and the hazard cascade that ensues afterwards. So the Hellenic subduction zone is in the Eastern Mediterranean. I'm highlighting the plate boundary here in red. What I want to note in this sort of zoomed out view is that the plate margin is pretty far south of the forearc high that's located in this location here. It's south of the accretionary complex, the Mediterranean Ridge accretionary complex that is here, but is often misidentified as this area of a deep bathymetric low here that I'll talk about in the next slide. This subduction zone is the largest, fastest, and most seismically active subduction zone in the Mediterranean, where the African lithosphere subducts beneath the Eurasian lithosphere at a rate of about 36 millimeters per year. Most of this subduction velocity is associated with rollback of the African slab, and smaller components of it are associated with slow convergence between Africa and Eurasia. The plate boundary is thought to accommodate convergence largely by aseismic creep, and this is known from seismic moment release records as well as GPS studies. So it's thought that the subduction interface does not produce large, devastating megathrust earthquakes, at least not frequently if it does. And the seismic potential of this region is poorly understood, as are the orogenic processes that are building topography in the subduction forearc and upper plate. So we'll zoom into this area here. So as I mentioned before, the plate boundary is located about 150 kilometers south of Crete here. We know that it's located here because the Mediterranean Ridge is north of it. There's a series of deep bathymetric depressions that are just south of Crete, located here, known as the Hellenic troughs, that are commonly misidentified as the subduction trench. However, again, the accretionary complex can't be south or away outboard of the trench. These trenches are certainly the surface expression of upper crustal structures, and they are thought to be the source, potentially the source of devastating earthquakes and tsunamis in the area. One thing I want to highlight about these bathymetric features, looking at this cross-section or two cross-sections from A to A prime, is that there is debate over the kinematics of these faults. One school of thought is that these bathymetric depressions are the result of extensional to transtensional structures that would go down through just the upper part of the crust, so they wouldn't be huge faults and would have lower seismic potential than another idea where these are the surface expression of reverse faults that splay up the subduction interface and cut all the way through the crust, which would have much larger seismic potential because the faults are much larger. Now, I'm not going to talk about the geodynamic implications of these different models. I just wanted to highlight that these different geodynamic models have really important implications for driving our conceptual understanding of what the seismic hazards might be in this area and other areas. So it's important that we understand the geodynamics to give context for how we interpret structures that aren't well resolved with geophysical data that are offshore, for example. So, as I mentioned, there's this long history of devastating earthquakes and tsunamis in this area. This area has been had civilizations here for millennia, and we have a really long written record that allows us to look back and say, okay, we've had large earthquakes, but we might not really know where those are sourced. Perhaps the best example of this comes from Western Crete, located here, where there is evidence of a really large earthquake in the historical record that's also preserved in the archaeological record that struck the area in AD 365. And there's been a fair amount of work on this because it's associated with a tsunami that radiated throughout the Eastern Mediterranean basin and famously inundated Alexandria, Egypt. Research on this earthquake by Beth Shaw and others, some really excellent research, suggests that the earthquake that produced this tsunami in 365 AD may have been a great earthquake, a magnitude 8.5 earthquake, which would be very large. They believe that it was sourced in southwestern Crete, and the rupture displaced the seafloor and generated this massive tsunami. Now, there's a lot of evidence of this. Part of it comes from the archaeological record that I'll talk about in today's talk a bit. Also from the written record, there's a lot of good documentation of past devastating earthquakes and tsunamis in this region that we can use to our advantage. But mostly what I'm going to focus on today is the geomorphology in Crete, and specifically looking at this Holocene paleo-shoreline that's highlighted in this image off to the right. What we have here, it may be kind of hard to see, but if you look from the shoreline up to the top of that white arrow, there's this little notch that you can see that in this location in southwestern Crete is 9 meters above sea level. It's about here. And this has been something that's been observed for more than a century, probably longer than that, and thought to represent uplift associated with an earthquake, so coseismic uplift associated with the shoreline. So we're going to focus a lot on this feature, but we're also going to integrate the written records and archaeological records into our interpretations. So this paleo shoreline in Crete is, if you go on vacation here in Western Crete, which I would recommend doing. It's spectacular. So this is what it looks like in different locations throughout the island, and its elevation changes depending on where you are. So we and many other groups have gone out and surveyed the elevation of this bathtub ring or this paleo shoreline, and you can actually contour out the amount of deformation associated with it. So what's shown here is just a map of Western Crete, and the black contours are representing the elevation of the paleo shoreline. So what you can see is that we have a northeast tilt associated with this, presumably this big earthquake event, with a maximum amount of uplift in the southwestern tip of Crete of about 9 meters, and it decays moving away from that. So this is a massive area that's been uplifted about 160 by 80 kilometers. And then locally, we have this uplift of about 9 meters. So this is a pretty impressive amount of deformation of the Earth's surface, or uplift of the Earth's surface. So people have done a lot of work on this. So there's been radiocarbon dating of marine fossils that indicate that this shoreline was uplifted around the 1st centuries AD, roughly. Because of the written records of the AD 365 earthquake, it's thought that this paleo shoreline was probably uplifted in that event. And people have since then been trying to figure out what the actual fault was that generated this amount of uplift. Early on, researchers thought that the uplift was related to the rupture of the megathrust. However, it's, as I'll show you in a little bit, it's beyond the megathrust likely being weakly coupled and not capable of generating these large earthquakes. Geometrically, it's not possible for rupture of the megathrust to produce this amount of uplift. So what we want to do in this study is figure out what the potential source or sources of uplift are and the associated earthquake sizes and where they're located. We want to explore what this means for earthquake and tsunami hazards in the Eastern Mediterranean. And then in the second part of the talk, I'll get into a little bit about the geomorphic consequences of these kinds of events, at least like sort of from a sideways, not directly. So this is some really good evidence that the uplift is not associated with rupture of the megathrust. This is, again, work by Beth Shaw from her dissertation, where she did some dislocation modeling to demonstrate that rupture of the megathrust would actually produce subsidence in the area where we see uplift associated with this paleoshoreline. And this is because the megathrust is simply too far south and too shallowly dipping to coseismically produce the type of deformation that we see. So this led her and many other researchers to say, okay, the fault's not the megathrust, it's got to be located closer to Crete, and it's got to be a upper plate fault. As I mentioned before, we have GPS data and seismic moment release records that suggest that the plate interface also slips by aseismic creep, so it's probably unlikely to produce these large events. So what we can say, I think, with a fair amount of confidence is that this uplift that we see in southwestern Crete and this 365 AD event are not likely a subduction zone earthquake. So what was proposed before to match this uplift pattern that we see from the deformed paleoshoreline using dislocation modeling was that this uplift all occurred during a single event. And in order to produce that type of uplift, what Beth Shaw and others proposed very cleverly was that there may have been an unrecognized splay fault, reverse fault, that comes off the plate interface and daylights in this deep bathymetric depression that we call the Hellenic trough that's located southwest of Crete. And it can reproduce this deformation pattern pretty well. And what it would imply is that we have a huge earthquake, a magnitude 8.5 earthquake needed to produce this amount of uplift. And they also demonstrated that this type of rupture would produce a tsunami that radiates throughout the Eastern Mediterranean, consistent with what had been written in the historical record. So this is a really clever idea and really exciting. However, there are some potential questions that remain about it. The first one is that this would be the largest reported earthquake in the Mediterranean region by a long shot. So it'd be a massive earthquake. It'd be one of the largest non-megathrust earthquakes ever recorded. And it would suggest that the tsunami and earthquake hazard potential in the Eastern Mediterranean is much higher than previously estimated. But as a geologist, what stood out to me is not all of these things, but really what stood out to me is that this would require a really significant change in stress regime of the forearc that has not been explained, was not explained in that paper and hasn't been explained since, where offshore, it's observed that there's a lot of extensional structures. Onshore, on Crete, there's only active extensional faults. And what this would imply is that there's been a geologically recent change in the stress regime from one where we have a forearc that's dominated by extension to one that goes into compression just south of Crete. And this period of extension extends from the mid to late Miocene up through the Quaternary. And then during the Quaternary, there would be some switch. And it's not clear what would cause that change in the stress regime in the forearc to produce this splay thrust or the splay fault. Now, these are maps here that are just showing some of the evidence of extension. So what we have in these areas that are highlighted in yellow are areas in the Mediterranean that have active contraction, definitive active contraction. And these areas that I'm going to highlight in red here are areas where we have active extensional faults that have been mapped on and offshore. And so you can see in the Aegean region that we're having this mapped extensional regime extend pretty far to the south, and the boundary between extension and compression, at least based on faults that have been mapped on the surface and submarine environment, suggests that transition, kinematic transition, occurs at the northern end of the Mediterranean Ridge accretionary complex. And there's also evidence from focal mechanisms that are shown before that upper crustal faults in this region in the Aegean are largely extensional to transtensional. So this pervasive upper crustal extension flies in the face of this idea that we have a contractional structure beneath Crete. But it doesn't mean that hypothesis is incorrect by any means, and just means that if this idea is correct, is that the source of this 365 AD earthquake stands out as an anomaly, and it may mean that we need to rethink our understanding of the geodynamics of the system. However, I think there's maybe a simpler hypothesis that we want to test in this study. Again, we're not trying to prove the other study wrong, but what we want to do is try to nullify another hypothesis that we have. Based on the work that we've done in the area and others have done, we know that all the active upper crustal structures on Crete, both onshore and in the near offshore, are all extensional. We know this from focal mechanisms. We know this from geophysics offshore. All the faults that are shown here in black, and they are all extensional faults. And some of the ones that are offshore are highly active with slip rates of 3 to 6 millimeters a year. So what we were interested in is to say, okay, we know that the uplift in Western Crete is sort of confined to this area, and then we have these huge extensional fault arrays that are offshore, located here and here. Can these produce the type of deformation that we see with this Holocene paleo-shoreline, this paleo-shoreline that was coseismically uplifted? So the hypothesis that we have is that maybe it's not just a single earthquake that produced the uplift that we see there, which was one of the underlying assumptions in Shaw, the work by Shaw and others. Instead, we suggest that maybe it was 2 or more earthquakes that occurred on observed active normal faults that uplifted the paleo shoreline. So we want to explore this idea because it's more consistent with the regional understanding of the regional kinematics of the structures and the geodynamics of the system, just to see if we can pull this off the table. If we can't nullify it, it suggests that this may be a viable alternative hypothesis. So the lines of evidence that we're going to consider are the geochronology and the archaeological and historical record to explore whether or not this uplift occurred in a single event. If it was a single event, it's got to be on a big reverse fault. There's no way you would be able to produce it on a normal fault with realistic rupture parameters. Can the deformation pattern, if we think it's more than one earthquake, be reproduced only by a reverse fault? Or is this something that we can reproduce by having 2 or more ruptures on normal faults that are adjacent to where the uplift is? And then the other thing that we want to see is if we think this can reproduce the uplift, can we generate tsunamis from the normal faults that are consistent with written records that come from Alexandria, Egypt, where there's some pretty detailed information on what the polarity of the wave and the run-up looked like. So the first thing that we did was compiled 72 existing radiocarbon dates that are at or below the paleo shoreline, and then we did 32 new radiocarbon ages. So we have more than 100 radiocarbon dates in and around the shoreline that we're working with. We went to 9 different sites, and from 9 of those different sites, we did vertical transects, going from the modern shoreline all the way up to where the paleo shoreline is. And the idea is we want to test if the data require a single earthquake to explain what the radiocarbon results look like. So I don't have time to go into all the details of what we did in this analysis, but I'll just go into sort of the synthesis of this. What we have here is a stacked probability density plot of all the individual radiocarbon ages that come from the paleo shoreline. This is demarcating the 365 AD event where we have a big peak. So this is definitely indicating that the 365 AD earthquake produced a significant amount of uplift. But we also have this big right skew in the data that suggests that the shoreline could have been uplifted a bit earlier than that, even as much as 3,000 radiocarbon years in the past. Richard did a lot of work to look at the historical record and identify that there's 7 to 8 damaging historical earthquakes between about 400 BC and 800 AD that are thought to be sourced in Western Crete. So these could have incrementally uplifted this shoreline. But I think most importantly, there's evidence in the written record of an earthquake that occurred in 66 AD in Western Crete that had evidence of a tsunami that people had recorded. And there's archaeological evidence in Western Crete that it uplifted a Roman age harbor that's located here that was abandoned in 66 AD because it was above sea level after the earthquake. So this is pretty compelling evidence that the shoreline was at least partially uplifted in 66 AD, possibly in other earthquakes. So what we get out of the radiocarbon data, the historical and archaeological record, is that it's extremely unlikely that uplift of the shoreline occurred in a single event. 9 meters of uplift is an enormous amount of uplift, and it seems more likely that it was at least uplifted in 2 events and probably more. So now that we think that we have a hypothesis where we can that allows for at least multiple ruptures, what we decided to do is some viscoelastic dislocation modeling. In one case, what we did was just say in one end member, we're just going to allow for 2 normal fault ruptures of faults in western and southern Crete and see if we can match the distribution of uplift associated with the paleo shoreline. And we can match it really well. And we get sort of, for normal faults, they would be really big earthquakes, high 7s. And with a fair amount of slip, but they're not totally crazy estimates. But again, this is an extreme case where we're assuming that the uplift only occurred in 2 events, and we think that it may have occurred in more. I think the most important thing that comes out of this is that we can match the distribution of uplift as well with 2 normal fault ruptures as we could with 1 reverse fault rupture, which is shown here. And the reverse fault rupture in terms of size, fault size relative to slip is anomalously high. And so we think that the normal fault data fits the results, the paleo shoreline uplift equally well to the reverse fault, but the rupture parameters that we get, even though they are high, are more realistic than what we would assume from the reverse fault model. So the last thing that we wanted to consider was, can these normal faults produce tsunamis that can radiate throughout the basin? So this is modeling that Richard did using the software EasyWave. And this is an animation of a normal fault rupture along the south coast producing this tsunami wave that goes throughout the Mediterranean. And one of the things that we wanted to look at was what the waveform of the tsunami wave looks like at Alexandria, Egypt, which is designated by the star, where we have these great written records of what happened there, and compare the 2 normal fault rupture wave run-ups to the reverse fault wave run-ups to see what we get. And this is because the written record suggests that we had a really, really big drawdown before the city got inundated. And so we want to see if the polarity of the wave is different for the different ruptures. This right here is the South Coast tsunami wave modeling of maximum heights, showing that we can generate waves that go throughout the Eastern Mediterranean basin on this type of rupture. What we're going to look at is the waveforms of the wave run-up. And what we basically get for the reverse fault model or thrust fault model is that we have a big run-up before we have the big drawdown. So this is not exactly what was described in the written record. But if we look at the normal fault models, they produce what was described, this big drawdown before the run-up. So this is sort of speculative, but it does suggest that the polarity of the waves from a normal fault appear to be more consistent with the written record, but we do agree that this is certainly not conclusive, but an interesting observation. More importantly, I think we find that we can generate pretty big tsunamis that go throughout the Mediterranean basin that are consistent with the written records. So the last thing I'll look at is the comparison with the long-term deformation of the forearc that we know from previous studies. So in the case of the upper plate reverse fault model, we expect these great earthquakes and tsunamis, and then uplift is going to be largely associated with displacement along the structure. So what we expect is to have the highest uplift rates right where the fault is, and then they'll decay away from the fault. Alternatively, we have this model where we have upper crustal extension. This upper crustal extension is driven by rollback of the African lithosphere that's stretching the upper plate, combined with underplating along the plate interface that over-thickens the crust, and then it starts to gravitationally collapse under its own weight, producing these extensional structures. This would indicate less severe earthquakes, but it would indicate that the uplift is occurring mainly through underplating of sediments, so this regional inflation signal that's going to be augmented by local movement on the normal faults that we see in this area. So this is work from Richard where he was mapping out long-term deformation patterns or uplift patterns associated with Pleistocene marine terraces. So these are integrating timescales of about 100,000 years or so. And one of the important observations that comes out of this is that he has very low or stable rates of uplift on this island of Gobdos, which is adjacent to the Hellenic trough here. This low amount of uplift that we're getting here is inconsistent with the idea that we have a reverse fault that's driving uplift in this area. If the reverse fault were driving long-term uplift over long-term, meaning hundreds of thousands of years, we would expect very high rates, the highest rates of uplift on Gobdos, and we simply don't see that. Rather, we have a pattern of uplift that's consistent with this regional, slow regional uplift that's augmented by displacement on these normal faults. And this is a pattern of deformation that is been playing out in the Hellenic forearc at least since the late Miocene and seems to be going on today. So what this implies is that we're not having this change in stress regime where this reverse fault comes in and is dominating uplift of the forearc in the modern. One other piece of evidence that I'll pull in here too is that there is not a lot of geophysical data offshore in the Hellenic troughs, but there was some drilling that was done in the late 70s and early 80s when they thought the Hellenic trough was actually a megathrust. And now we know that that is not the case for various reasons. But work by a French group in the early 90s compiled that existing data and showed that the borehole data is actually consistent with the Hellenic trough being a southwest dipping normal fault, and that data is located here. So we don't think that this is a reverse fault. We do think it's a normal fault, but there's still a lot of questions that remain there. So if this alternative hypothesis is correct, what it implies is that normal or possibly transtensional faults embedded in the upper plate in the Eastern Mediterranean are the primary seismic hazard. And we expect earthquake magnitudes that are less than the high sevens. These are still pretty strong earthquakes and they can produce tsunamis. So it's still dangerous, but not as dangerous as previous studies suggest. One thing that I didn't highlight too much in here, but the historical record and archaeological record point to is this data implies that earthquakes in this region are clustered in time, meaning that if you have rupture on one extensional structure, it can change the stress regime on another, pushing it closer to failure. And then we may have clustered earthquakes similar to what we see playing out in the central Apennines today. So this actually has important implications for how we might evaluate earthquake hazards as a function of time and where we are in a different type of earthquake cycle than we might expect on a megathrust, for example. However, I'm the first to admit that what I presented to you is not entirely conclusive. And if people are to do future work, we need geophysicists to do a lot of the work and get proper seismic reflection data south of Crete. Private companies have already generated this data, but it's not released. So we could really clarify the kinematics of those offshore structures if that data were released or somebody got access to it. which would have really important value in discriminating between the two different hypotheses that I presented today. We also need work that bridges timescales from long to short to be able to come up with a consistent, cohesive geodynamic model for the region, which helps inform our conceptual understanding of what the types of faults might be, both on and offshore, and what their seismic potential is. And there would be a lot of benefit in raising public awareness of tsunami hazards in the Mediterranean, where I don't think people are that well educated on it in the region. All right, so the conclusions are that the Holocene shoreline on Crete likely uplifted in more than one event. Uplift of the paleo shoreline can be reproduced by rupture of two known active normal faults, and the normal fault tsunamis appear to better match historical records. Earthquake and tsunami hazards are still high, we would suggest, if our hypothesis is correct, but are lower than some estimates. And we think that our normal fault model that we propose is more consistent with the longer term geological record and what we know about the geodynamics of the system. All right, so now we're going to zoom into the small area and still in Western Crete. We're going to change gears, and what we're going to do is think about geomorphic hazards and geomorphic hazard cascades. And this is work done by my former master's student, Elena Bruni. And I decided to pull this in because I think it's a really cool case study of hazard cascades that can be used as a potential example for studies elsewhere throughout the planet where there's similar processes playing out. So where we're going is this small catchment called the Klados catchment, located here. If you're familiar with Crete, this is just west of the Samaria Gorge, which is located here, which is one of the deepest gorges in Europe. The Klados catchment is a small catchment. It's about 12 kilometers squared and drains carbonate rocks. And it has these really spectacular coastal fans that are located here that are really thick. Now, what got us interested in this is that the fans are really, really big. And we had done some work on Pleistocene fans nearby, and the fans in Klados are distinct in terms of their morphology, in terms of their sedimentology, and I think most importantly, pedology, meaning their soil characteristics, relative to these Pleistocene fans that I'm just showing two examples that are just to the west of this area. And this is what the stratigraphy and soil development looks like. The Pleistocene fans tend to have decent soils. The Klados fans have almost no soil on them at all, suggesting that they're very, very young, Holocene in age, very likely. So the questions that we have are, why are the fans so large and apparently young in Klados? So what's causing them to form? And then what does this mean for our understanding of landscape dynamics, or think about it as geomorphic hazard cascades above subduction zones? So the approach that we used was pretty basic geomorphic mapping, where we did a lot of mapping, looking at cross-cutting relationships and other features in Klados. And then we use this information to understand the dynamics of the catchment and its implications for surface hazard cascades. And again, this is led by Elena. This is Elena looking at one of these deposits in this catchment. So this is mapping showing the primary geomorphic units in the southern part of the Klados catchment and Klados Gorge. And I'll spare you some of the details for the sake of time, but we identified three primary geomorphic units. The oldest one is a large, previously unidentified landslide deposit that's in blue. The next oldest is this upper fan that's highlighted in red, and a series of fill terraces that propagate up the valley all the way to the headwaters. And then inset into that is this orange, a lower fan unit that also goes upstream and grades into these fill terraces. There are other geomorphic units that are secondary that I'm not going to talk about. It's not that they're unimportant. They are also interesting, but not for the story I'm going to tell you today. And there are really beautiful cross-cutting relationships between these different geomorphic units that allow us to establish a relative chronology of events in really great detail. So I'll go through what these look like, and we'll just look at a bunch of photos because it's pretty nice. So we're in the map I'll show you where we're looking from this vantage point over towards this landslide deposit here. This landslide deposit is locally more than 100 meters thick, and you can see this sort of weird erosion of this deposit forms this pedestal type topography. In detail, the landslide deposit is a matrix supported amalgamation of pulverized carbonate, which is what we have in the matrix, and then these chunks of bigger pieces of carbonate. And the landslide fills a pre-existing paleo topography. So it goes over paleo hills, it blocks paleo tributaries. In fact, what we're looking at here used to be the outlet of the Klados Gorge, and then it was dammed by the landslide deposit. So it dammed it here, and then it diverted it in this direction. So it used to actually drain out this way, but it no longer does that because of this landslide deposit. Inset into the landslide deposit are these two different fan units, and we'll be looking from this perspective in the next image. So from down here, we have this upper fan unit that's here. It's at its apex about 60 meters thick. Inset into that is this lower fan unit and associated terraces that I'll talk about a little bit. This lower fan unit clearly buries the notch associated with the uplift that I talked about before. So it's definitely younger than that earthquake in 365 AD, or at least that's what's inferred here, meaning that it's very young. The last couple thousand years, could be even younger. Stratigraphy from these fan units indicates that they are triggered by some external event. So we have each of them is characterized by a very high energy basal debris flow deposit, and then unsteady aggradation or unsteady deposition after that through time. So series of events that occur afterwards that are also in some cases debris flows or flash flood type events. And there's a crude fining upward sequence in both of these fan units, indicating that, or at least our interpretation is that you're getting exhaustion of sediment supply through time as you go up in the section. Those fans connect with terraces that go up valley. So this is a longitudinal river profile going from where the fans are here and moving upwards. And we find patches of the landslide all throughout the valley as we go up valley, as well as these fill terraces that go all the way up to the headwaters for both the lower and the upper unit. And having terraces that go this far up valley in a catchment this small is highly unusual. Typically, we'd find terraces lower down in valleys, and certainly not as thick as what we see in a catchment that's only 12 kilometers squared. Another interesting feature of the terraces is that we have straths, or the basal unconformity of these different features that is exposed. And we actually get vertical unconformities, or what are referred to as buttress unconformities, that demonstrate that the river had actually cut down below the landslide into bedrock before the upper fan aggraded, and then it incised through the upper fan down into bedrock again before the lower fan aggraded. And these terraces are really thick and fill in a paleotopography. So this is one example of the upper fan unit, T1, that has this really unusual unconformity because it's backfilling a pre-existing paleotopography. So these unconformities have a relative chronology that's really interesting. We have this big landslide deposit, and then we have incision through that deposit into bedrock. Then we get deposit of the upper fan and associated terrace, and then that cuts through that deposit and then back into bedrock. Then we have aggradation of the lower terrace and fan, and then incision again back into bedrock in the modern. So highly dynamic and unsteady phases of incision and aggradation in this catchment. Again, this is just showing some of this filling of the paleotopography. So this very irregular bedrock contact associated that is beneath the upper terrace, indicating that it really aggraded a big part of this valley, which is really neat. Some more relative chronology. So now we're at the coast looking at the contact of the lower fan with that notch that I'd mentioned in the earlier part of the talk, just to get a good idea of what these different cross-cutting relationships look like. We can see that the notch goes behind this fan. You can see this located here. Another interesting thing is that we have these marine shells that are located here, and they're sort of caked by the fan unit. What this indicates is that this fan is younger than the notch that's here, which is a great constraint that we have. So this lower fan clearly buries this shoreline that was uplifted by the Holocene earthquake or earthquakes. It also appears that the upper fan is probably younger than the shoreline, but we couldn't conclusively demonstrate that with cross-cutting relationships, but it appears that that's the case. And so this indicates, if this is correct, that the upper and lower fan are both Holocene and deposited within the last few thousand years. So the catchment aggraded and incised over the last few millennia, which in terms of geomorphic dynamics is quite remarkable considering how thick these deposits are. The relative age of the landslide relative to this uplifted shoreline is unclear, but based on the lack of soil development in stable components of that geomorphic unit, it appears to be very young. So it also appears to be Holocene in age. And we were able to do some radiocarbon dating, largely on soil carbon, which isn't the best target to use because the soil can develop over millennia. And so you can get a big distribution of radiocarbon ages, and they're always going to be older, and in some cases, much older than the actual deposit. The results are shown here in sort of like a table format, which isn't ideal, but the data is really messy. The key thing that comes out of this is that all the data is Holocene, so it's consistent with our interpretations. Some of it is out of order in terms of the radiocarbon age with respect to what we know about the relative chronology, which isn't too exciting. But nonetheless, it does place each of these geomorphic units firmly in the mid to latest part of the Holocene, indicating that these are really young units. But we would be better served by having better geochronology on these deposits. So what's going on in this catchment? So there's evidence from the field that suggests that there is a big recent rockfall highlighted up here. So the headwaters of the catchment, we have this old exhumed fault that's here that forms this really steep cliff. And at the top of the cliff, we have what looks like a very active cliff face that probably could have had detachment of rock that came down and produced the landslide deposit that we see. And Elena did some reconstructions of hypothetical detachment sizes from this cliff face, somewhere between 1 million and 1 billion cubic kilometers of rock, depending on what she thought detached. And that is within the range, or at least the order of magnitude range of what she reconstructed for the amount of sediment that would have been in the valley in the past at some point in time, which is about on the order of 10 million cubic meters of sediment that were in the valley at some point. So the idea that we have is that we have detachment of some cliff face here that goes down this about 700-meter drop down to the valley bottom. So we have some detachment here, drops down this, the rock mass pulverizes and then swoops down the rest of the valley. So to test that, Elena did some landslide modeling using Dan 3D Flex and landslide modeling software. And what she found is that if she had a failure of roughly 90 cubic meters of rock mass, that 90 million cubic meters of rock mass that detaches from that surface, that she can match the extent and thickness of the observed landslide deposit that we have. So we think that this is pretty compelling evidence that we have a big rockfall that occurs, comes down, hits the base of the cliff, and then translates into a sliding mass or a cloud of mass that backfills this entire valley. Now, what we basically think happens, the interpretation here is that we have a large landslide or rockfall that was likely triggered by those Holocene earthquakes. And this deposits about 100 meters of material throughout the valley. And this is highly erodible material that completely alters the sensitivity of this system to external perturbations, meaning large earthquakes or large storm events. The catchment sort of stabilizes a little bit after the landslide event and sizes through it. And then we have some other perturbation that could be an earthquake. It could be a high magnitude rainfall event that drives aggradation of the upper fan unit that fills up. Then it incisors through that. So things stabilize again when the sediment source is exhausted. Then we have another event that causes the aggradation of the lower terrace. And then we incise through that. So what this suggests is that that initial hazard, that initial rockfall altered the state of the system, making it much more hazardous and much more sensitive to external perturbations. Now, all of this is occurring within, we think, probably several millennia. And the system is still adjusting. So that sediment supply that was produced by the landslide or rockfall still isn't exhausted. So this catchment is completely different, still completely different and sensitive to perturbations in ways that it wasn't before the event. So the conclusions from this part of the talk are that small catchment dynamics can be altered by catastrophic mass wasting events. The system that we studied after this event occurs alternates between phases of aggradation and scission that we think are related to large-scale perturbations, so earthquakes or storms. And this is really important, I think, because landscape dynamics is going to be determined by the legacy of past events. And so what's important to think about is that we studied this catchment in Klados, and it may respond completely differently to an earthquake than the Samaria Gorge, which is right next to it, in large part because the Klados Gorge is backfilled with a lot of sediment and has the legacy of this past event. So its initial conditions are different when that event occurs relative to adjacent catchments. So it can explain different sensitivities in the landscape based on those initial conditions. And I think what comes out of this, to tie it back a little bit to the first part of the talk, is that this suggests that upper plate earthquakes can perturb landscape systems or geomorphic systems for up to millennia, which, if we think about a lot of events, we think about how they perturb a landscape maybe for decades, maybe a century. But in some of these high magnitude events, they can perturb the system for thousands of years, which I think is really important. So if you don't take anything else away from the talk, what I'd want you to take away from this is that upper plate faults pose significant seismic hazards and can trigger large tsunamis and mass wasting events that we need to consider when we're studying subduction zone geohazards. And land surface hazards can perturb geomorphic systems for millennia because they'll alter the state of the system. The other things that I want people to take away from this, these maybe should have been labeled 3 and 4, especially for the SZ4D community, is just to consider upper plate faults in studies that we're doing because they're critically important, particularly for hazard interactions and hazard cascades. And then the other thing I want to highlight from these two studies is that they're both studying sort of the ancient record. And studying the ancient record is a really useful complement to rapid response studies. So we can use these case studies to understand earthquake hazards. We can use these studies to understand landscape response to perturbations and hazard cascades afterwards. But be able to look at them in different ways than we would with rapid response studies that are really, really wonderful complements. So with that, I will stop talking and open the floor to questions.
Thank you so much, Sean. That was a great talk. And we already have a question in the chat from Juan Gonzalez, who says, Thank you, Sean, for the excellent presentation and for sharing these significant advances. I was wondering if you have investigated the application of Coulomb stress change modeling to assess cascading activation of crustal faults following megathrust earthquakes.
I have not. I have not, but I think other researchers have, um, because they must play an important role, especially in the in the stress regime of the upper crustal faults after before and after rupture of the megathrust. I think in the case of Crete, because of the megathrust there being probably uh, creeping rather than sticking. I think some of these Coulomb stress models just for the interactions of the upper crustal faults would be really interesting to explore, similar to comparable studies that have been done in the central Apennines in Italy.
Thank you so much. We have a question from Athanasios Ganas, who says, Great talk, Dr. Gallen. Thanks. A recent study by Robertson et al. In Western Crete uses 36 CL dates also showed that mean uplift rates increase towards the east and not towards west, as Shaw et al.'s splay model would indicate. But we cannot rule out that the megathrust is active, as we have numerous evidence for low angle thrust faulting south of Crete with P axis normal to the arc. Definitely needs more research and more field data. I agree. One question has to do with the preservation of the 9-meter notch versus higher notches. The higher notches can be also explained by upper plate extensional faulting.
No, partially. So that's a great question. So what we're looking at here actually, this is actually good to clarify for the people that are watching that may not be familiar with it. This is an image that's in Western Crete, and this feature that I'm highlighting at the bottom is the coseismically uplifted notch, and then there's a bench here and there's a bench here. These benches are all, and there's one over here. Those benches are also paleo shorelines or fossil beaches that are uplifted over a longer time scale. So they are uplifted, typically in this case, probably tens to hundreds of thousands of years. And so in this case, part of them is uplifted on the normal fault, or at least some of the uplift signals associated with that. Um, but it can't explain the uplift of these features over the long term and on normal faults alone. And this is because normal faults embedded in the upper crust over the long term are going to thin the Earth's crust, and they're going to lower mean elevations in that case. So if we just assume that there are normal faults in this area only, we can get a little bit of local uplift in the footwalls of those faults. But over the long term, the entire island can't be uplifting because it's riddled by these normal faults, some of which are very large. And so the interpretation that we've made based on the uplift of marine and river terraces that are found in grabens or areas that should be subsiding based on normal faults, but they're actually uplifting, is that there's a deeper signal of uplift. This could be on a reverse or thrust fault that's been unidentified that's offshore south of Crete, but our preferred interpretation is that it's associated with duplexing and folding of material deep within the Earth's crust in the lower part of the crust due to accretion of material or underplating of material beneath the forearc, and that's what's driving the net long-term uplift of the forearc here. At least that's our interpretation, but it's not been conclusively demonstrated at this point.
Thank you so much. We are now at the top of the hour, and so I want to remind everyone that this webinar will be recorded and uploaded to the SZ4D YouTube channel. So if you want to rewatch it or send it to your colleagues and rest of your community, please feel free to do so. And if any questions come up after the end of this webinar, feel free to email us and we will pass them along. Thank you again, Sean, for such a wonderful webinar and for taking time out of your day to participate in this webinar series. And thank you to everyone who joined. We really appreciate your time.
Yeah, thank you.
Thank you. Have a great rest of your day. Bye.